Okay, now we are going to talk about the distribution of means. Don't compare a sample mean directly to a distribution of individual scores, as that's a mismatch. Now, why does this happen? Let's first look at how it's formed. You take a random sample, compute the mean, repeat numerous times to form a new distribution. What do you do is when we're talking about the distribution of means is you have 10,000 balls in a pit. You take 50 of those balls and then you compute the mean of them. The mean number, I guess. Those balls have a number written on them from 1 to 10. I don't know. So you take that, you compute the mean. What does it come out to? 4, maybe. You do it again, it's 5. You do it again, 7. You know? You keep doing that again and again and again and again and again, and then you graph those means into a theoretical distribution here, like this. This is the distribution of means. So, in your samples, in this theoretical distribution of means, it's going to end up almost the exact same as your population table because the means will just average themselves out. You see, this is a fundamental rule that will be asked in the exam. The distribution of the mean of the distribution of means and the population mean is exactly the same. I don't know if I could explain it well because I don't comprehend that well, but it's just the same. If you see M and this funky U, mu, next to each other, just know that they are equal to each other. That's all you need to know. When we are trying to get the variance of means, we do standard deviation of the population squared. So we get the variance of the population divided by the number of samples we have. So we are working with samples now. Distribution of means, I don't know what that is, but I just know that we are working with samples. The amount of scores you have, you divide it by them. For example, you have a sample of 30 scores. So you take the variance, which is the standard deviation squared, of your population, and then divide it by 30. It gives you your variance of means. Because we divided it by 30, we essentially just toned down the intensity of that variance. Because when we just do it the normal way, if we used the population's parameters on our 30 sample, then it would be too intense for it. Because think about it, when you have a sample, there are more likely to be extreme scores that are not normalized by the amount of data you have. Normally, if you have an outlier of 100, for example, there could be an equal amount of 0 values. So it would land you towards the middle at 50 in a population because it's so much data. But since you only have 30 samples, you have to tone things down. This is why we divide it by the amount of data we have in the sample, the total scores. So to get the standard deviation of means, we just do standard deviation of the population divided by the square root of the samples we have, of the amount of total samples we have, n for short. We call this the standard error. We call it an error because it's just how wiggly our data is. If you repeated the same sampling process multiple times, this standard error would give you approximately how much your results would vary. I don't know if it really makes sense, but if our population looks like this, then our distribution of means could look like this. In this case, our standard error could be 3. You know, how many standard deviations our data is from the normal mean of the population. Think of it like this. Your standard deviation is like a key. It's like a token. It's like an ID for your original data, for your population. With that ID, if you apply it to anything, you can do easier maths. We call the standard deviation a form of spread in statistics. It's just how spread or how your data is spread out. It's like the ID number of your dataset. We can use it on the z-scores. We can use it for comparisons. So just think of it like that. We are taking the standard deviation because it's a unique identifier for our original population. And then we are taking the square root of n, and then we get the standard error. The reason we take the square root of n is because it essentially forces us to do this operation. So what was our formula? This is sigma divided by square root of n. To actually convert this, to actually, I guess, complete this operation, what we need to do is we need to square this. We now have a normalized n, and then we take the square root of all of this. Now, this function is quite similar because, as you can see, this gives you what? This gives you the variance of the mean. What is this? This is the variance, this here. And what happens when you take the square root of a variance? You get the standard deviation. And then this lends us the standard error. Just if you see sample being mentioned, if you see m instead of mu, then you're working with a sample and it turns into a standard error. As we said, if the population is there, if original population is already normal, or your sample size, or yes, if your sample size is higher than 30 or like 31, your data would get approximately normal. So if you're doing a research, try to aim for 30 people or more. How do we apply z-testing? We define the null and alternative hypotheses H0 and H1. We then determine the comparison distribution. What is it? We take the mean and the standard error for the distribution of means based on the sample size that we have. We have the mean and the standard deviation because a holy power is going to give it to us in the exams, usually. If not, we will use confidence intervals, etc., but we will get to those. We established a critical z-score or threshold to reject a null hypothesis, as we discussed. Because this is a one-tailed, we will use 1.64. And then we determine the sample's z-score. What is it? It's mean minus the universe mean divided by the standard error. That's a handful. Is it the standard error? Probably. It should be at least. Oh my god, I forgot. It must be. If it's not, I'm gonna, I don't know, die. Yes, standard error. Oh my god. I'm sorry. So what was it? It's z equals, oh, I forget. M minus mu m, like this. And was it minus or times? Divided by the standard error, which is normally used like this. That's why I'm getting confused. These symbols don't make sense. Calculate the z-score. This is how you compute the z-score. So this m here should be the mean. And this here should be the population mean. We have these information because it has been given to us by holy powers, as I stated. This is your sample mean. And this is your population mean. Yeah, you get it. So sample mean minus population mean divided by standard error equals your z-score. I hope I am saying it correctly. I'm getting quiet because the symbols are not matching up. Like, this is not defined anywhere. And I don't want to give any wrong information. Let me just double check this. This is so embarrassing. Yes. It was correct. I don't know if I can edit this video. I wish I could. I wish I had the time. Anyways, I hope you skipped like 5 minutes or something. I don't know how much that took. There is ongoing debate in the field about p-values that fall between 0.5 and 0.10. Some say it's strict, some say it's not. Some are more flexible by saying that this cutoff is arbitrary. Some say it's meaningful. Some say no, you must. It's not. It's worthless. Your research is worthless if it doesn't fall into less than 5%. Okay. So where were we? We calculated the z-score. And then we compared the sample z-score to the cutoff point to decide whether to reject the null hypothesis or not. So let's say our z-score was 2, which is more than the cutoff point of 1.64. Therefore, we can reject the null hypothesis, which is great. As we said, there is a strict view towards probabilities, and there's a flexible view. Now, this is the actually very confusing part. We don't know the population mean, usually. We don't know mu. We only know the sample mean, which is our best estimate for the population mean. Researchers often rely on the standard error and the confidence intervals. So the confidence interval is true population mean. It's the range where the actual population mean is expected to fall into. So if you have, let's say, a data, a mean, let's say it's 1, you can say that I am 95% confident that, judging based on this raw score of 1 that I have, it will fall between 50 and minus 50, you know? Who cares? No, I care because if there's a zero in that range, your argument is automatically invalid, which is interesting. You're basically taking your mean and then you're expanding it. So this is your mean, okay? This is the mean score that you got, which lands somewhere down here if we have data. You're saying that in the true population, it would land here or here between these two values. This is what confidence interval is. So if your results fall outside this, then you can say, yes, this is significant because it's outside of the mean range. Everything in statistics serves the same purpose and many different purposes. I don't understand. But it essentially means that if your confidence interval is higher, like 99%, it means your data needs to be in the 1% in order to be statistically significant. Makes sense? Perhaps. It makes sense in my head. I hope I was able to explain it well. It just gives you a probability of where the true population mean would land. The actual data rarely reported directly. They usually report the means and the standard deviations, and standard error is also commonly displayed visually in graphs as your error bars. I guess we need to see some of these graphs because I don't understand anything.